diagram. So we've got the ridge up here. We have the top plate of the wall, and we have our rafters spanning from ridge beam down to top plate. Okay? The span of the rafter is from there down to there, and it should be taken to the outside edge of the timber frame. The bit that hangs over is called the overhang. Okay? And the overhang is important in the design of a rafter. It does contribute to the instability, if you like, of that rafter. And so we need to consider the overhang when we're sizing it. Okay, so the first thing that you would do is to determine the wind classification for your building. And for Sydney, that's going to be N1 or N2. I didn't tell you about the wind classifications. N stands for non-cyclonic, and it's divided up into 4 different groups, N1 to N4. And cyclonic has C as the prefix, so C1 to C4. Okay. As you go down in number, N4 becomes stronger winds. So N1 and N2 is probably the lowest of the wind classifications. You would next determine what your dead and live loads are on the rafters. So what sort of a roof do I have on here? Is it sheet roofing? Is it tiled roof? And for a cathedral roof, you would need to consider the ceiling loads, because a cathedral roof is built this way so that you have high ceiling. Okay, and the ceiling is actually attached onto the bottom of your rafters. So these rafters will be taking the roof material, roof battens, their own weight, insulation, sarking, whatever you've got there as well, and then your ceiling load as well. Okay, you would then determine the rafter span. This example they're saying that is 2.1 metres or 2100 millimetres, and it's a single span. Okay, from there to there is single span. You can't consider this to be continuous because there's no other support. You then determine the rafter overhang, because this creates a cantilever and it adds extra load. So here we've got an example where it's a 500 millimetre overhang. You would also need to know what the rafter spacing is, because obviously if your rafters are closer together, then you can have a smaller size for the same loads. Alright? 600 spacing is a fairly regular spacing, but it might be 450, it might be 900, it might be 1200. Okay. So then we would go to our AS 1684, volume 2, which is for non-cyclonic, winds N1 and N2, and we go to the rafter span table, which is number 29. Okay, so table number 29 is for rafters, and the one I've given you is not MGP10, I'm afraid, it's F7, because later on in the example we're going to do is with F7. But on the top right-hand corner, you'll see the stress grade. This table is for. You'll see what the wind classification is, and then 2. What type of timber this MGP10 is. It's seasoned softwood. Okay, it's seasoned radiata pine. This is actually 1999 code. The ones I've given you are the 2010. It'll say AS 1684.2, N1, N2. So they're lumped together. And the supplement number, this is supplement number 4 for MGP10. Supplement 2 is for F7, seasoned softwood. So, and there are, I don't know how many supplements, lots of them. Now this is table 29, which is always the table number for rafters or purlins. Now that's not under purlins. It's just another name for a rafter in a slightly different situation, okay? So there's what the table looks like, and for rafters, it'll have all this stuff at the top here and down the side that you will need to know. That's all the information you need to know in order to look up what size you need. So here we're looking at a rafter spacing, okay? We were told the rafter spacing was 600. That's there, and there's another 600 over here, okay? But these are for single span versus continuous span. Our rafter was single span, okay, so we're on this side of the table, 600 spacing. Now, if we go down this column, can you look here, we've got span and we've got overhang under the 600 spacing, all right? So down this column, we've got spans, and down this column, we've got overhang. Now, you need to look at the size of your timber, which is listed on the side here, 70 by 35, 70 by 45, etc. Because for each size, there's this roof and ceiling mass, kilograms per square metre. All right, so it's allowing you to choose what type of roof mass you have. So a very light roof covering, roof sheeting, would be 10 kilograms per metre squared. So that might be like just sheet roofing with some insulation. But ours has got ceiling loads as well, and we've got 60 kilograms per square metre. So we would be looking at this row in the 60s, okay? And we go down this column until we get a span of 2100 and an overhang of 500. Okay? And this will give us, when we get to that point where we satisfy both of those requirements, that'll tell us what size we need for our rafter. Okay? So that's for MGP 10. And it's going to give you different sizes depending on what grade. Now you've got F7, which is probably quite similar to MGP 10. It'll have slightly different numbers, but you might come up with 90 by 45 as well in your table. Alright, so that's how the tables are used. Choose the right table for the right type of timber. Choose the side of the table, single span versus continuous, and then use the information to read off what size member that you need. Any questions on that one?
Yeah. The span, you said 2100, is that usually specified, or is that sort of average?
No, that will be, you will be working that out, or whoever's designing it will be working that out from the dimensions of the house and the pitch of the roof. Okay, so let me just show you that on the board here. Okay, this is a fairly simplified diagram. As I said before, the rafter sits on the outside edge of the timber frame. So this is just a simple diagram, so I haven't shown the bird's mouth or anything. But the rafter span is measured from the ridge down to the outside edge of the timber. Okay? And now we had a cathedral roof there, so we didn't have a ceiling joist tying it together. But the principle of working out your rafter span is the same, basically. Is you need to remember your trig functions, sine, cos and tan, and then it's just working out some dimensions. So usually on your house plans, you'll have a dimension of the house, and typically for a timber framed brick veneer house, you'll have an external dimension, right? The width of the house, which will be to the outside edge of the brickwork, okay? So that might be, say it's 8 metres. Alright? Your roof is spanning from there to there. From outside edge of timber frame to outside edge of timber frame. So you need to start with that dimension that you had. You need to know how thick your brick veneer is and what sort of cavity you have to work out what your roof span is to start with. Okay? Now, a brick width, do you know what a brick width is?
100 mil.
110. 110 is a standard brick, single skin. And cavities are usually around 50 mil, sometimes 60, sometimes 40. Okay, so 110 is the brick width and 50 cavity. Alright, so at this end you would have to subtract 160 mil from this measurement, and also at the other side to get your roof span figure. Right, so this number up here is going to be 8 metres minus 2 lots of 160. Yeah? So what would that be?
768.
Yep, 768, good. Alright, so that's pretty easy, isn't it? So up on our triangle up here, if I break it into two halves, because I want that dimension there. So if I just drop, okay, so that's not actually a roof member, but it's just breaking this up into a triangle with a right angle there, because that's a horizontal, that's perpendicular, so we've got a right angle triangle there, and that dimension, the base of the triangle now is half that figure. Yep. So 3,840. Yep. Okay, now we would normally know the pitch of the roof or the rise of the roof. And if we didn't, then we could read it off the elevation drawings, okay, and work out the rise of the roof. So let's say we have a standard sort of 25mm pitch, and the pitch is actually stated somewhere. So what do we do that if we want to find the raft span? Do you remember your trick?
So cos?
Cos? Okay, so what does cos give me? Do you remember?
Adjacent over.
Good, adjacent over hypotenuse. And if you remember the other relationships, there was sine.
Opposite over hypotenuse.
Yep, opposite. So you might need any one of these relationships in doing these calcs, these preliminary calcs that you need. So tan is the last one. That's right, opposite over adjacent. And there's a little rule about how to remember, or a little, what do you call those things?
Mnemonic.
Mnemonic. For remembering that. Does anyone have one?
Sokotoa.
Anyone, any others? Oh. So, Toa. Okay. Julia, you have one, don't you? It's yours? No, same. Okay, so Sokotoa, sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. Or make up your own mnemonic if you like. So those relationships are very useful to know. So, but how do you apply them? Okay, well, if you have a triangle like this with the right angle there, the hypotenuse is the one that's opposite the right angle or the longest side. Okay, that's the hypotenuse there. Now, which is the opposite and which is the adjacent? That depends on which angle you're wanting to get this sine, cos, or tan of. So in this case, I'm looking at that angle there. So if I call that angle theta, okay, if I wanted sine theta, or if I wanted anything to do with theta, the opposite side is the one over there, and the adjacent side is the one down here. Okay? If I was looking at that angle up there, the opposite would be this side down here, and the adjacent would be that one. Okay? So for this one, adjacent, so that's adjacent to theta, and this is opposite to theta. Okay, so in this triangle I want to find the hypotenuse, and I have the adjacent. So I want cos. I want to use cos. Cos of my angle, 25 degrees, equals the adjacent, 3840, divided by the hypotenuse, which is my rafter span. Okay? Now, if that's the thing I want to find, you have to have a little bit more of your maths, drag that back from year 10 or 12 or whenever. Rearrange the equation a little bit so that rafter span is over this side and it says rafter span equals. Alright? So for those of you for whom it's been a while or you never quite got it, you need to, this is the bottom of a fraction, you need to multiply both sides of the equation by that in order to get rid of the fraction.
Transportation.
Yes. So multiply by rafter span, if I could just put it like that, multiply by rafter span. If I'm multiplying this, they will cancel, and I end up with rafter span times cos 25 equals 3840. It's still not ideal for me. I like to have rafter span equals. So now I have to get rid of that bit. So I divide both sides by cos 25. Then they can cancel. And I end up with the rafter span equals 3840 divided by cos 25. And that I can just put in my calculator. Alright, so I won't do the whole that throughout today because I'm assuming that all of you are pretty comfortable with that, but if anyone isn't, you know, just call me aside at lunchtime or something. Okay, so then we put that in the calculator. $3,840 divided by cos 25 equals, I've got to get my glasses on. 4237. Now, you know the number's going to come out to be bigger than this one. because it's the hypotenuse and it's a longer distance going up the slope than straight across. So if your number comes out less than that, go back and have a look what you've done wrong. All right? So there we have our rafter span, 4, 2, 3, 7. Okay? So our rafter span is not something we can just look at the dimensions. We have to calculate it. You will also need to work out your overhang in the same way using that cos. Okay? So if you look at the overhang, you will probably be given an eave dimension. Say it's 500. And the eave dimension is usually measured from the outside of the building, from the edge of your brick, to the edge of your eave, to the fascia. Okay? And it's measured on the horizontal, it's not measured down the slope. So how do we work out the overhang? Now the overhang is not from there to here, it's from there to here. Alright? So for your overhang, you need to look at that dimension, which before we subtracted, now we have to add. So the 110 of the brickwork and the 50 cavity, we add to the 500 because our overhang dimension is that. Oh, sorry, that's wrong. It's a very bad word. We need that measurement 500 plus 160, so 660. And the overhang will be equal to 660 divided by cos 25 degrees. Okay, because the triangle it's very similar to the one up there, with the base dimension being 660 and this being the overhang. Okay, so the triangles are just the same, except the base of our triangle is now that dimension, so we have the same equation, 660 divided by cos 25, which is 728. Okay. Now, something about overhangs. Sometimes overhangs don't have to be considered in sizing the rafter. Okay, so imagine this is our rafter. It's bird's mouth into our top plate there. This is a wall stud. And we have this overhang of our rafter. Okay. Sometimes the rafter is tied back into the wall frame. So sometimes there's a timber member something like that, which is bolted back into the wall frame, and that stabilises the end of your overhang. and provides additional support. So if you have this situation, which is called the overhang is tied back, then in those tables you can ignore the overhang figure. So all you're looking for is the span of your rafter, and you can just ignore whatever the overhang is. Don't even bother working it out. All right? Now this is quite common, and you wouldn't see this tied back in a finished building because it would have some fibrous cement sheeting under there. Oh, there's your brickwork up to there, and you've probably got a little scotia there. So all you'll see is the underside of your eave. You'll see some lining. Okay, but that doesn't necessarily mean it's tied back, because sometimes what happens is you'll have a soffit bearer, in other words a timber member that you can attach your lining to, but it just sits from a little hanger and you apply your lining onto that. Alright, now that's not tied back. That's not tied back to your wall frame, and so this thing is still flapping around. Okay? So in this case, you would still need to consider what your overhang dimension is in sizing your rafter. Any questions?
Would they leave the gap like that?
No, sorry, there's your brickwork.
Oh, sorry.
Okay. Right, let's go back to this then. Away from rafters for a moment and talking about bracing. And of course bracing is resisting wind loads, so it's resisting those wind loads which produce braking forces or racking forces that can cause overturning, sliding, structural collapse. So bracing is put onto the walls and also into the roof to stop all of those things happening with wind load. Okay? Wind loads on the roof are resisted by roof bracing, and that transfers the loads to the ceiling, and that is transferred then to the top plates and into the walls. The walls therefore have to resist deformation due to the wind loads, and they tend to resist wind loads by having bracing panels or cross bracing in them. And I'm sure you've seen those two different types of bracing in walls, and the little model outside has some bracing panels on it, but you'll see, whenever you see a building going up, you'll see panels being used and often the cross metal bracing.
What's the difference between structural and nominal bracing?
Structural bracing is bracing panels, steel cross bracing, timber cross bracing, and bracing, and nominal bracing is when you count the bracing that's created by wall linings, such as your internal wall linings. So the fact that your internal wall linings are attached to all your studs and produce that effect that it won't distort gives it some inherent bracing capacity, but it's nominal.
Is that like cladding on the side of a
Yes,
Well.
cladding can do the same. Some cladding is actually designed to be bracing, to be structural bracing as well, which I think might be a little bit dangerous if you don't know that that's what it's for. Whereas most structural bracing is obvious what it is. It's not part of the cladding of the building, etc. But yes, cladding can also contribute to bracing strength. Okay, so these are just different types of bracing: sheet bracing, cross bracing, roof bracing, and subfloors. If the subfloors require bracing, they can have cross bracing as well. Probably don't see very much of that. So that's to illustrate what happens when you put bracing onto the walls, is that you're trying to reduce the effect of distortion of your members. So if you imagine this sort of structure connected with nails, a nail at each joint, you'd expect that structure to be quite stiff, but if you have a single nail at each of those joints, you know that that sort of structure with rectangles, if you hold the bottom of it and put a force up on the top left-hand corner here, it'll just, it just folds up, doesn't it? So that kind of situation happens quite easily. So the idea is to put a flat plane on it to make sure that none of the members can distort relative to the others, or to put a diagonal brace on it. Okay, so if you put a diagonal brace from here to here in this structure, or from that joint to this joint here, and then you put a lateral load on it, this member would immediately go into tension and acts to hold the whole structure together. So that's how your diagonal braces work, and then your flat ones act like a whole diaphragm.
For walls, is it 2 nails per stud?
Generally, for your bracing, it's 2 nails per stud, but for all the different types of bracing, AS 1684 tells you exactly what size of nail or fixing and how many of them and where they need to go. So that's illustrating, again, the diagonal brace. So when you have diagonal bracing, obviously the wind comes from all directions, so you have to have two. One brace in this direction. When the wind comes from this direction, it will go into tension. That's good. But in the other direction, the wind in the other direction will put it into compression. And these members tend to be slender. They might just be a steel strap that's 1 or 2 millimetres thick. So if you put it into compression, it just buckles immediately. So you need to have the diagonal in the other direction as well, so that you have the 2 directions covered. Okay? So when you have a look in AS 1684 and it shows you a single diagonal, read the fine print, because it will say it has to have a matching pair going in the other direction.
And what about the spacing of those diagonals? 1.8 or?
Well, it depends on the height of the wall, because the angle is critical. Yes. So often it's 1.8 is the minimum, and 2.7 is the maximum. And that's usually for a 2.7 high wall. So I think that's from 30 degrees up to 45 degrees. And you can't go below the 30 degrees in the angle for your bracing. And you can't go higher than that. Otherwise it becomes quite ineffective. So obviously 45 degrees is probably the optimum. Okay, so when you're looking at bracing, you need to know what the wind classification is. You need to work out what the area of the house, of the side of the house is that the wind is pushing on. Because the wind applies a pressure to a surface, okay? So the wind blowing onto the side of a house is blowing onto that area. And so in determining the amount of bracing in your building, you need to be able to work out the area of an elevation. So you would need to be able to draw an elevation from a floor plan, although of course when you get your plans you'll have the elevations already there. Okay. So working out an area from an elevation is pretty easy. It's usually only rectangles and triangles. But you need that area because the wind is given to you in pressure. So AS 1684 gives you the wind pressure on a certain face of a building, on all the different faces in fact, so that you can work out the pressure and area, you can work out the total force. Okay? And you need to know the total force because you need to put in an amount of bracing that can resist that amount of force. So we'll do a bracing count this afternoon. I'm pretty sure we'll have time to get one more. So to have a look at some bracing and the fixings, putting bracing panels into the walls is not sufficient because think back to those different situations where you've got overturning. Okay, so you actually lateral loads on the side of a building can also cause an uplift sort of effect, can lift the floor of the building. So in addition to having those panels that resist it distorting, you need to tie everything down. So there are tie downs, fixings required along with your bracing in order to make sure that things don't still topple over. So all fixings at joints must be able to resist gravity uplift and horizontal forces. These might be nails, they might be straps, bolts, screws, coach screws, framing anchors, steel washers. Okay, and there's a picture of a few of the types of tie downs that you have. So typically a metal strap such as that one, this is a metal strap as well, and there's also a connection between the rafter there and the top plate. There's a holding down bolt in the bottom plate of the wall frame into what looks like a concrete slab, but could be, yeah,